Greetings and welcome to this lecture on semantic and discourse analysis. In this session, we will explore word embeddings and word to with SIBO and skipgram and the model GLOVE. We will begin by understanding word meaning and gradually learn how computers represent words numerically for natural language processing applications. This is Dr.R.Usharani, Assistant Professor, Department of Computational Intelligence, SRM Institute of Science and Technology, KATANGALATHUR. Before we begin, let us look at the learning objectives of this lectures. By this end of this session, we will be able to understand the concept of lexical semantics, word embeddings, numerical word representations, word to WIC and its architectures such as SIBO and skipgram, and the model GLOVE. Next, we can implement and analyze word to WIC based word embeddings using Python. Let us start with the lexical semantics concept. It is nothing but it's a study of the meaning of words and the relationship between words in a language. Consider an example, the words teacher and instructor. Although the words are different, they convey a similar meaning. Similarly, we can consider another two words, laptop and computer. These words are semantically related because a laptop is a type of computer. So human understand this easily, but NLP systems need semantic analysis to identify correct senses. So we need to way to represent words meaningfully. For example, a single word may have multiple senses. Let us look at these examples. The student gathered in the class before the exam. Here the meaning of the word class is a classroom used for teaching. Let us consider the second sentence B. The teacher praised the class for their discipline. Here the class meaning is a group of students, although related, but the word is interpreted differently based on context. Consider another example also, sentence A. She opened a new account in the bank. Here the meaning is she created an account or opening the bank account, which is equal to bank record. On the other hand, another sentence B, the witness gave an account of the incident. Here the meaning of the word account is description or report. The same word has different senses we can understand from these word sentences. Again, we can remind ourselves human understand this context, but NLP systems need semantic analysis to identify correct senses. Therefore, we need a way to represent words numerically. Okay, so what's the connection between lexical semantics and word senses? Here, the lexical semantics is the broader study of word meaning. On the other hand, word senses are part of lexical semantics that focuses on different meanings a word can have. So, lexical semantics and understand word meaning. Next, identifying different word senses. Let us consider another example also. Please book a table for 4 people. Here, table means furniture. Another sentence. Display the student data in a table. Here, table means a structured arrangement of information. Again, we remind ourselves, human understand this easily, but NLP systems need semantic analysis to identify the correct senses. So we need to understand the need for word embeddings and numerical word representations. Numerical word representations is nothing but to enable computers to process text, words can be assigned numerical positions. Let us consider this example. Word with positions are tabularized in this picture. Here the three words cat, dog and car. Consider the position 1, 2, 3. So these positions represented the computers to store and process words numerically, not directly with words. But the limitation consider here is the computer may incorrectly assume that dog is closer to cat than car because 2 is the numerical number 2 is closer to 1 than 3. The numbers do not represent the actual meaning of words. Therefore, simple numbering is not suitable for capturing semantic relationships. Here, what's the solution? The solution is one-hot encoding. So, what is one-hot encoding? We need to understand. It is nothing but it's a binary representation of a vector. So, consider this table example. Here, cat with unique binary vector 100 we have, and the second row indicated the word dog with 010 unique vector representation, and next one car with 001. Even if we are using one-hot encoding, it cannot capture semantic similarity between words. Consider the example. Cat and dog are semantically similar, which means animals. Cat and car are semantically different. So here, one-hot encoding treats all words as equally distinct. So we need another need for word embeddings. It represents word as dense numerical vectors that preserve semantic meaning and relationship between words. So what is word embeddings and how it uses the dense numerical vector representations of a word? While one-hot encoding solves uniqueness problems, but still it failed to capture semantic similarity between words. Therefore, we are going to learn word embeddings. Word embeddings is a dense numerical vector representation of a word that capture its semantic meaning and relationship with other words. So, unlike simple numbering and one-hot encoding, word embeddings place semantically similar words closer together in a vector space. But how it is possible? The vectors shown in the example are manually assigned values. They are learned automatically from the text data by a model such as word2vec. Consider this data. Here the three words are there: cat, dog, and car. Cat embedding vector represented here is 0.85, 0.72, 0.10, and the word dog represented the vector 0.82, 0.75, and 0.12, and the car represented the vector 0.15, 0.20, and 0.91. The yellow color highlighted here is cat and dog nearly close to the same dense vectors. 0.85 and 0.72, 0.10 is closely related to the next word dog, 0.82, 0.75, 0.12. But considering cat and car, there is much difference, many difference between them, these two words, cat and car. So here the observation is cat and dog have similar vector values almost. Car has different vector representation. Therefore, semantically related words obtain similar numerical representation. From this, we can conclude this. So, where we can apply this word embeddings are widely used in chatbots, machine translation, text classification, sentiment analysis, question answering system, and information retrieval. So, hope you understood the need for word embeddings. The next question is, how can a computer learn these meaningful word vectors automatically from large text collection? This leads to word to vector. We know about that, but how it is possible? How are these vectors obtained? By the use of two techniques, CBOW and skipgram. So before understanding the technique CBOW and skipgram, consider the example. How are these vectors obtained? The cat drinks milk. First sentence. The second sentence, the dog drinks milk. The cat eats fish. The dog eats meat. The model observes that cat and dog appear in similar contexts. Both occur near words such as drinks, milk, eats. Therefore, during training, the model learns similar vectors for cat and dog. So conceptually, the cat dense vectors 0.85, 0.7 to 0.10. The word dog vector 0.82, 0.75 and 0.12. Since the vectors are similar, the model infers that the words are semantically related. So, this word to vec uses this word corpora like that. So, in this technique, word to vec uses two architectures, SIBO and skipgram. Uh, why we need SIBO and skipgram? Anyway, word to vec is a neural network model based technique. It is used to learn word embeddings from large text corpora. So it converts word into dense numerical vectors while preserving semantic relationship between words. The main idea of word to vec, words appearing in similar contexts tend to have similar meanings. Anyway, we have already seen this example. The cat drinks milk, the dog drinks milk. Word cat and dog occur in similar context. So by processing millions of such relationships, word to vec generates meaningful word vectors. How it is possible? By these two architectures, CBOW and skipgram. So these architectures differ in how they learn word relationships one another. First, consider the CBOW, continuous bag of words. It predicts a target word using its surrounding context word. Let us look at the example sentence. The cat drinks milk. Suppose the target word is cat, let us assume, and our input context words are the word the, drinks, and milk. Output target word cat, we have seen already. And so context words to target word is the A. Here the context words are the plus drinks plus milk. Here the output target word is cat. So intuition here is if we know the surrounding words, the dash drinks milk. Here guess the missing word is likely cat or dog possible. So SIBO learns this relationship during training. On the other hand, skipgram, it predicts the surrounding context words using the target word. That is a reverse case of the SIBO. So consider an example, the sentence, the cat drinks milk. Suppose the target word is cat. So input target word cat, output context words are the, drinks, and milk. So target word to context words, now cat to the, drinks, and the milk. Here the intuition is given the word cat, the model tries to predict the words that usually appear around it. So we can easily remember this. SIBO means context to word. Skipgram means word to context. Let us consider the another model, GLOVE. It is nothing but global vectors for word representation. That learns word meanings by analyzing how frequently words co-occur with one another in a large text corpus. Unlike word to vec learn from local context windows. On the other hand, GLOVE learns global word occurrences, otherwise word co-occurrence statistics to generate word embeddings. So GLOVE observed that cat and dog often appear in similar contexts. Consider the sentences: the cat drinks milk, the dog drinks milk. The cat eats fish, the dog eats meat. So both occur near words such as drinks and milk. Therefore, their vector representations become similar. So we can understand all these techniques, the implementation of Python program. So consider this Python program. First, we install the GenSim. So why? Because we can import word to vec model from the GenSim library. Therefore, we are install this GenSim, and we can import this word to vec model. So here I am using the small sentences only, but actually large data set corpora, large language data set otherwise known as corpora, that we can use it here is possible. You can fetch any data set from online resources and use it here. For our easy understanding purpose, I am using these small sentences in this example. Here the sentences contains the word cat drinks milk, dog drinks milk, cat eats fish, dog eats meat, all this. So next we need to train the word to vec model. How to do in Python? By the use of word to vec function. Here we need to incorporate sentences, that is input text data we have already defined in this sentences. Next, word vector size is 5, which means each word is represented by 5 numerical values. You can increase, decrease as possible. Window size is 2, so number of neighboring words considered as context. So if we change window equal to 3, then neighboring words, 3 words can be considered. And the next, minimum count 1, including all vectors appearing at least once. Next, skip gram equal to 1. If skip gram equal to 0, then we can go with above also possible. And display the numerical vector representation of the word cat, then we can print the word cat. So we are using the model dot VW of word vector of cat. Okay. Similarly, we can print model dot word vector most similar. Next one, similarity between cat and dog. So model similarity cat and dog we are using here. So what's the word vector for cat? This is generated from word vector, word to vec. Okay. So next, word similar to cat, the words dog with dense vector representation from word to vec technique, milk with this value, fish with this value, eats with this value, etc. Okay, drinks and other words. So similarity between cat and dog is 0.0726 something else. Okay, so hope you all understood all the concepts from this session. So the key concepts we have seen in this lecture: lexical semantics, it studies word meanings and their relationships. Word senses help identify the correct meaning of a word based on context. Word embeddings represents words as meaningful numerical vectors, and word to vec learns word embeddings automatically from text data, and it can use two architectures, CBOW and skipgram. CBOW predicts a target word from context words, while skipgram predicts context words from a target word. And another model, gloves, it also generates word embeddings by analyzing global word occurrences statistics in a text corpus. How we are using word to vec in our Python programming. Similarly, you can try your own Python program with this glove model also possible. At your own time, you can try this. So thank you for watching.